Hello, my name is Nathan Hadaway, and this is my Lab 5 constant force experiment in Physics 1. So what is this lab? Well, this is a lab where I took a kind of expo marker eraser and I slid it across a table. This is very similar to the first lab, if you remember it, where we took a track and we slid it across a frictionless track. Um, However, here there is friction. There's a very noticeable friction between the table and the eraser. So we can measure that and kind of prove that friction is a constant force, but we'll get more into that next slide. I set the origin to be the beginning of the meter stick, which you'll see when I play the video that we took, and the positive x direction in the direction that the eraser is moving. So there's no need for y direction because the eraser isn't moving in that direction. Um, just to clarify, that is kind of from the right-hand side of the screen to the left-hand side of the screen. I set the system to be the eraser and the surroundings to be everything else. Earth with its gravitational pull, table with its normal force and friction force, and air, which is basically just saying anything else that exists in the universe. So here is the video that we took of the eraser. Go. Pretty simple video. Then we tried to simulate this in GlowScript. You can see this is probably the most important part of the code in the bottom right-hand corner. If you want to look at the rest of it, the URL is right there beneath it. You can see here, though, that I added in a coefficient of friction and a friction force in the negative x direction. And then I also added a starting velocity. Last thing that I did was compile the real world and simulate data to see how they compared. So what is the lab trying to prove? Well, it's trying to prove that friction force is a constant force and acts in the opposite direction of motion. Um, it's This is seen from the equation for friction force, which I didn't put on the slide, but it is friction force is equal to coefficient of friction times mass times gravity, or acceleration due to gravity. You can see here I said friction based on the normal force opposing gravity, because there are other types of frictions, like when holding a water bottle up, when you're holding the sides of it. Um, what's keeping it from falling down is the friction force of your hand between your hand and the sides of the water bottle. But we're not dealing with that. We're dealing with friction force that opposes gravity, and since acceleration due to gravity doesn't change, and the mass isn't changing, and the surfaces aren't changing, meaning the coefficient of friction isn't changing, then the force is constant because every part of it is constant. So this lab is trying to prove that. It is also trying to prove the velocity update formula shown here, v final equals v initial plus F net over m times delta t. You can think, if F net is constant, mass is constant, then velocity final should increase or decrease linearly, depending on if the force is positive or negative. Here it's negative, so we should expect for velocity to decrease linearly. We're also trying to prove that with an initial positive velocity and a opposing constant force, the object will eventually stop. That just kind of makes sense, Opposing force means that the velocity will dissipate. It also shows that the displacement update formula, here it'll show this because we know that the velocity is decreasing linearly. Using this equation, which is a first order, pretty simple equation, we can expect that the final velocity will decrease quadratically, which we do see in the top right hand corner, which is the simulated graph of position. Here we have some more graphs where we compared the real and simulated data. A couple reasons for error is human error. We can really see this in the velocity versus time graph because when the computer takes a derivative to get the velocity, then it kind of exaggerates the mistakes made from human error. So you can see the blue line is much more jagged in the velocity versus time graph than the position versus time graph. A couple assumptions made was there's no air resistance, and the only force acting, or the net force of the object is the friction force. All the rest cancel each other out. And I also the friction force is always in the negative direction, which you can see. Especially, I used to have a longer time period, but you can see right at the end of this time period, the red graph for position versus time graph kind of seems dipped down, or I guess it's easier to see in the velocity versus time graph. You can see at the very end it gets negative, which doesn't make sense for velocity because velocity at that point it is making the object speed up in the negative direction, which friction force does not do. It opposes the motion, so it would just stop at 0 meters per second. Some frequently asked questions is like, what if the axis was flipped? If I made it in the negative x direction, really wouldn't change anything. It would mean that the initial velocity would be in the negative direction, and so then friction force opposing that would be acting in the positive direction, still slow it down and stop at a negative x displacement away from the origin. instead of a positive displacement or a positive in the positive direction. Now, how many forces that I really account for? Now, I technically account for three forces, these being obviously the friction force, but also there's a force of gravity normal force exerted on the eraser. However, these are at equal magnitudes in opposite directions, so they cancel each other out, leaving a net force of friction. There are, other forces technically acting on it, but they're so incredibly negligible that I didn't account for any of them. Thank you for listening.